Hi there, and welcome to my project video. I'm Scott Newton, an electrical engineering PhD student at Columbia University. As technology becomes highly scaled, design constraints are becoming more and more difficult. It is likely some sort of automated physical design methodology will be required to design analog circuits in the future. This project researches the feasibility of using standard cells and automated digital design tools to design analog circuits. To that end, a continuous time analog fourth order low-pass Butterworth filter was exclusively designed using standard cells specified in Verilog HDL code and auto-placed and auto-routed just as any ordinary digital logic circuit. The chip was fabricated and lab measurements show almost identical performance as simulation results. However, dramatic time savings in physical design and layout are gained.
Here is a photo of the die. This photo shows my test assembly, including the PC board I designed and the chip I designed. The test platform includes two signal paths. Each of the two paths pass through the chip, and one path passes through the filter and the other path does not. This allows us to measure the performance of the filter without the effects of the interface circuitry. The power connector is on the lower left. The signal connectors are on the top, and the serial interface connector is on the right. The serial interface supports trimming of the cutoff frequency in 11 discrete steps. My chip is the ceramic 28-pin package towards the bottom. Various laboratory setups were constructed to measure the filter's performance. This photo shows a simple setup where a signal generator passes a 10 MHz signal through the filter, and it is monitored at the oscilloscope. The 10 MHz tone passes through the filter unattenuated since it's in the passband. This photo shows the laboratory setup to measure the magnitude frequency response of the filter. The laptop on the left is the user interface for the Copper Mountain network analyzer. The laptop on the right runs MATLAB code that controls the Arduino board, which drives the serial interface. To measure the cutoff frequency trim range, the MATLAB code cycles through all 11 trim steps. In this video, we can see the cutoff frequency being trimmed throughout its entire range in 11 steps. The MATLAB code continually cycles through these 11 steps, and you can see the cutoff frequency rising and falling with those adjustments. The trim range is from 10 MHz to 18 MHz, with the nominal setting being 13 MHz. The magnitude frequency response for each of the 11 cutoff frequency trim settings is plotted in MATLAB in this diagram. The uniformity of the trim settings and the trim range are clearly visible. And now, a brief discussion on the chip design. This analog continuous time fourth order Butterworth low-pass filter was constructed based on a RLC passive component prototype. Since inductors and resistors are rather large in silicon, they are replaced with active circuits. Prototype filter resistors are replaced with unity feedback transconductors, and inductors are replaced with transconductor-based gyrator C active inductors, as shown in the diagram. The filter input and output signals are differential, and a shunted inverter provides a common mode voltage source for external interfacing circuitry. And now to transconductance amplifier topology was chosen since it's solely constructed of inverters, which are common digital logic gate standard cells. The filter is implemented with 4 main capacitors. 11 smaller capacitors can be connected in parallel to these main capacitors using transmission gate switches. The enablers for the transmission gates are controlled by a serial port interface. The serial port interface consists of a simple shift register and parallel load register. A host connected to the interface can control the trim setting by shifting in control bits. Standard cells were designed for the transmission gate and capacitor so that they may be auto-placed and routed. This filter design was completely specified in HDL Verilog code. Here's example code of a now-to-transconductor amplifier implemented solely in Verilog code. To limit the parasitic effects of long traces, the design was floor planned using the cadence encounter tool. Floor planning allows us to constrain the placement of major modules so that the distance between them is minimized and therefore the trace lengths are also minimized. Floor planning also allows us to lay out major modules in signal paths symmetrically for differential signals. Each box in this floor plan diagram constrains the placement of the major modules within the top level HDL design. Critical areas of the circuit, such as the TCAs, are constrained close together around the center of the die, whereas less critical circuit components, such as the trim capacitors, are constrained on the outer edges of the die. Notice the symmetry around the center horizontal line. That provides the symmetry for the differential signal paths. The standard cells specified by the HDL netlist and physically constrained by the floor plan are automatically placed and routed using the cadence encounter tool. For this filter design, the auto place and route took less than a minute, and the floor planning took about an hour. Lab measurements show that the performance of this filter is nearly identical to simulations of the schematic and also of the parasitic extracted design. It is estimated that a traditional manual physical design would take days, if not weeks. Therefore, using this automated methodology can yield dramatic time savings for physical design and layout. I'd like to thank MOSIS for their generous contribution of silicon under their educational program. I'd also like to thank Professor Peter Kinjit for his expert guidance on this design, and also Sarthak Kalani for his expert teaching assistance.